Hi, folks. If you're listening, just any questions you have, please post them in the comments. All right. I think that'll do. Just testing the audio for a second. Hello there, this is Alan Abelson speaking. I'm one of the instructors for Math 121. We're ready to begin the session whenever you're ready. If you have any questions that you'd like to start with, please feel free to let me know in the comments. And we'll get started as soon as we see our first question. Sure thing. Just saw the post there from Pendle. Absolutely. Would you like to start with one of the questions from the practice problems, unit 8-ish, I guess? Or is there a specific exam problem you'd like to look at instead? Sure thing. So question 3 and 4 from exam 2016. Just give me a second to bring those up. CBS one, so look at that. Full screen. 3. Oh, sorry, the multiple choice question is 3. Okay, I think I'm looking at different questions. Question 3 from 2016 is an optimization question, so correct me if I'm wrong. And the other two for that same exam are just pure integration, no trapezoidal rule. Please feel free to type in correction if I'm looking in the wrong spot. I'll take a look at I'll bring the other exams up too, just so we have them. Oh, no, those two. So yes, Pendle, if you could let me know which questions I'm looking at that are not the ones you're thinking of, we can take a look at that. Multiple choice questions, okay. For the 2016 exam, neither of, again, maybe I'm looking at the wrong exam, but neither of those look like trapezoidal rule. Let me just take a look at the main campus version. I didn't think they were particularly different that year, but maybe that's the issue. Same questions. Okay. Yeah, so those aren't trapezoidal rule questions. You can let me know which one, maybe I'm looking at the wrong exam. This is the 2016 exam right now. I'll just boost up the size here. That's question 3 about formulas for the graph. And the previous page was the question, which is about the definition of the derivative, just recognizing the limit that we're computing there as a derivative. Right. Oh, Lord. Sorry, I saw one earlier one from 2011. We, generally speaking, don't go back that far simply because the solutions aren't posted. Some of the stuff that we covered in previous years, when you go back 7 years, isn't relevant. So if you meant 2017, let me know, but that was for, you just roll out screen there. I think it was Amy or someone. Oh, okay, sorry. I thought you had a question about trapezoid, and this wasn't trapezoid, which was throwing me off. Okay, so we'll start with Pendle's question. I'm just going to make a note of the other ones as they go by, so we'll return to them, and you'll know what order we're doing them in. So Amber, trapezoid question. Again, so I won't go back as far as 2011, but simply because most people won't have looked at it, so it's not as helpful for everyone else. But 2016, sorry, I got two mixed up, my apologies. Question 2016. which are not about trapezoidal rule? Okay. Sorry, just trying to get back to the earlier comments here. So if there's one from the practice problems for the trapezoid rule, I can't imagine, or one from the more recent exams, we certainly have used it repeatedly. So if you can find an example that's a little more current, I'd be happy to go over that. Right. Okay, so we'll start with Pendle's. Question number 3 from 2017. Right here. 2017. Multiple choice 3. So you're being asked to look at a limit, delta x goes to 0 over delta x, and 2 plus, yeah, to the 4 minus 2 to the 4. So the key ingredient here is there is recognition for this one, for sure. And the recognition is if we were at some point 2 and looking at some point just to the right of it, that would be the point 2 plus delta x. And so what we see here are 2 x values. I'll write it as a word to not confuse the numeral we're using here. 2 x values that are then getting subbed into some formula. So we're taking it to the power 4, and then we're dividing by delta x. So what that looks like, one of the forms we've seen before, is f of x plus delta x minus f of x all over delta x, or the similar form with h's, but we already have delta x's, so it feels like the definition of the derivative. This is one function value minus another function value. Oh, that's 2 y values. So I'm taking a change in f and dividing it by a change in x. Well, that's going to be a slope. So it's definitely a recognition thing. We don't expect people to look at this formula and see what it is immediately. But if you do, then you realize, oh, anything over delta x where I have a base value and the base value plus delta x, then we're looking at a derivative calculation. And so what this is f prime of x, f prime of 2, more specifically, when your function, well, if we go back to our actual calculation here, we took the 2 and took it to the 4. Well, that's what we see in our function is whatever our x value is, we run it through the function, it'll be x to the 4. We had 2 specifically. If we're going to do it in general, we take our input to the 4. Our input is 2 plus delta x. We take it to the 4, and so on. So let's take a look then at the options in the question. So you can compute the limit. Basically, we're looking for the numeric value here. Other questions of this type have different formats. But here, if we're just looking for the derivative, you can then say, okay, so f prime of x, just taking the derivative, is 4x cubed. And f prime of 2 is going to be 4 times 2 cubed. That's 4 times 8, that's 32. So once you get to the recognition of what the function is, it's straightforward. The biggest challenge is recognizing that construction as being a derivative. And basically that boils down to remembering your formula for the definition of the derivative, which is that guy there. You know it's f prime of 2 because it's actually a combination. There's the 2 and the 2 plus delta x. Those are your x's and your x plus delta x. So those are you look for the base point and the base point plus a little shift. If you see the same value in both of those, I see a 2 and I see a 2 plus delta x, that gives you the point reference that you're looking for exactly. Okay. Let me just go a different page here. Taking a look at 2017 multiple choice number 4. That was one of the graphical analysis questions. And I haven't quite got the screenshot capture going in, but what we can do is look at the period, and the period is going to be 1 pi. So actually I can do a quick sketch here. There, yeah. Through 0. Okay. There we go. Minus pi over 2 to pi. And so the period is the main thing here, or certainly one of the key ingredients. The period for one full cycle, it would start up again if we kept going. One cycle is pi long. And so the period is 1 pi. And then when we have a function like sine b times x, the period for that is 2 pi divided by whatever that number is. I'll put it in color here to highlight it. And then we just fill in the blanks. So our period is 1 pi. 2 pi over b is the relationship to that multiplier inside. Cancel the pi's, bring the b up, and you get yourself b equals 2. That's a very mechanical way to do it. The other way, which occurs to some people, is the natural period is 2 pi. And we've compressed that, down to 1 pi. Well, that's a compression by a factor of 2. That means we're looking at something like sine bx. That's how we would construct that formula, sorry, sine bx with a specific value of 2 in there to capture that compression by a factor of 2. So both of those give us the same scaling factor. Number 2, sorry, I saw Theo's note. 2016, number 2. Yep. All right. The other element, I think, is a shift. So we've got these shifts in here, and knowing what we know, the answer is going to be either A or C. And my best advice is don't overthink it. Plug in some numbers. You have the graph, you have a formula. If you take a look at sine of 2x minus pi, and you evaluate that at x equals 0, we know the value of our graph is 0, so it should be pi over 2. We know our value for the function is 0 there. If we plug that into our function, we get sine of 0 minus pi. That's sine of minus pi. Check it with a graph, check it with a calculator, whatever you'd like. You do get a 0 for that. Versus, that was A. C was the other option. 2 pi minus pi over 2. If you plug x equals 0 into that, sorry, 2 x's, then we're going to get sine of minus pi over 2. And that, if you plug it into your calculator, is -1. And that would rule out that because you want your graph to have a value of 0. That's good. We don't want a value -1. So that would point us towards A for that graph there. And yes, I got this right. Yeah. So that would be the correct value. You could also double check at later points just to make sure. But 1 point here is enough to rule out the alternative answer C. All right. Let me just do a flip back here and see if I missed any comments. Because for some reason, there we go. Yes. For some reason, I'm only seeing the most recent comments, and there's no see other comments, which is freaking me out a bit. Let me just try it on a different screen here for a second. Let's go do it. Sorry, still exploring some of the details of the Facebook Live construction here. Well, that is tremendously unhelpful. All right, so I can see the most recent 5 comments. If anyone has any advice for a relative Facebook newcomer about how to see more, but I'm not seeing any. I'm not seeing the usual button that says, more replies to this link. So I'll try to capture them as they come in. So we got Theo, and then I'll do Anshel's question. The integral of e to the 7x sine of 2x. All right. But Theo's question first about 2016, number 7. Let's take a look at that exam. 2016, number 7. Oh, I apologize. These are 2016. I got my questions wrong here. This is 2016. 2016. All right. All right. So just to confirm. Okay. So this also has a flavor of slopes in it, similar to the earlier derivative question. The best guide for this is to look back at the end of Unit 7 where we did optimization. So that would be my first guide to this. All right, just sorry, I saw Amy's note there. Unit 1, 32, 55. Unit 2, 922. Okay, I've got those down. All right, so the key thing for this problem is to recognize what h over t is or how you can see it on the graph. So I won't be able to do a perfect sketch of that graph, but it starts there and goes like that. All right. If you have the graph or the value h of t over t, from Unit 7, we don't expect you to be able to have discovered this on your own. This is not obvious. But if you do take a look at it, there's a construction you can add or an interpretation you can add to this. This is a y value, and this is a t value or an x value horizontal. What we can do without changing anything is subtract 0 from the top and 0 from the bottom. Nothing changes when we do that. What we get from doing that, though, is we get a new interpretation. If I think of the distance now, this is one y value minus another y value, that's a delta y. And on the bottom, I've got t minus 0. Well, that's a change in t value. But where's my point? Well, if I pick, let's go all the way out here to t, and I'm going from t to 0. So that's this whole gap here. That's a run. On the vertical side, I go from 0 up to here. That's h of t. That's what it means to be a function value. It means to start counting from 0 and going up to your graph. And then this is the slope of a line between the point 0, 0 and a point on the graph. Because the points on the graph have exactly the structure, hey, what's my t? That's my independent variable value. And then what's the corresponding y value on the graph itself? Oh, I'm answering the wrong question for you. I just saw that you were commenting about that. All right. So anyway, this is 2016, number 7. For those who care, we'll finish it off anyway because we're here. So the idea is you connect those values with a straight line. And if you choose different points, you get different slope values. The question asked, where do we get the largest value for this ratio? Pardon me. There we go. The question was, where do we get the largest value for that? We connect the straight lines, and I think in this case here, you actually get A as the steepest slope when you connect the point on the graph back to x equals 0. All right, seeing as that wasn't the question you asked, though, let's go back and find number 2 here. Hold on. Okay, so this is the straight derivative question. 2016. Okay, just confirming this is fall 2016 derivative question. Okay, let's go for it. All right. New question. Number 2. All right. So this hopefully is a straightforward derivative question. Is there a particular obstacle to this one? Finding the derivative of 3 to the 2x plus 1 of x to the 4. Sorry, my voice says you got to have your derivatives. Like there should be no, this is actually meant to be an easy, right over the plate kind of question. The only thing that people would typically make a technical error on is remembering the slightly more obscure derivative rule for non-exponential bases, non-base e bases. So fortunately, the rule is pretty simple. If it's x is in your exponent, then the derivative is the same function again. Then you take the derivative of your exponent. But there's this little gotcha, which is because this is not e, we end up multiplying by the ln of that base. That's the completion to the derivative of non-standard bases. So the derivative of e to the x is e to the x. The derivative of 3 to the x is 3 to the x times ln of 3. Now, those actually aren't different rules. They're just the same rule, but ln of e ends up being 1 every time, so there's nothing fancy about it. So, okay, sorry. That's why I'm trying to confirm the questions earlier. I saw your note there, fall 2016 CDS. Sorry, there are minor variations between the on-campus and the distance exams. That might be the question here. There we go. So let me be more precise. If you're asking about a particular exam question, if you can specify whether it's the main campus exam or the distance exam, whichever course you're in, that'll help narrow down the issue. All right, now that we finally tracked down your question for this one. This is, okay, this is essentially a test of geometry. So the key thing is you've got x squared plus y squared equals r squared for this whole circle. Literally, if you just draw, I shouldn't say just, not just, but if you draw this, the answer comes out. You got a point here, it's the point x and y, and you've been told that x squared plus y squared equals r squared. Actually, a similar flavor to the previous question with the slopes. How do you see this on the diagram? Well, your x coordinate is here, but another way to think about that is actually the distance from 0 from here to here. If you say I'm at x equals 2, well, it means I'm 2 to the right of 0. Then for the y value, it's the same thing. So the transition there is to interpret your x and y coordinates not just as points, but as distances. As soon as you say that, well, Pythagoras tells you that this diagonal, this hypotenuse, has to be length r. So that's your relationship. And then if you're trying to go back in the question and find out what the value of x is and what the value of y is, knowing the angle in this part here, then the beautiful thing is this is trigonometry. Cos of theta is adjacent over hypotenuse, which is x over r. Oh, well, if that's the case, I can just isolate for the x, and x is equal to r cos theta. And I'll try sine next just to see what happens. That's opposite over hypotenuse. So being careful, the opposite is over here in the y direction. And then you get y over r. Well, again, you isolate for y. That just means bringing the r up the other side, and you get y equals r sine of theta. If you have any friends in engineering, I would ask them about this. They had this drilled into them 16 ways in the first 3 weeks of class. But that leads you to this nice simple formula that on a unit circle, your x value is your cos theta, your y value is your sine theta. If you make it a circle with a different radius, then all you've done is made the radius a bit bigger. You're going to make the x and y coordinates bigger by the same amount. So this would point you towards, where are we here? D as the final answer for this one. Okay, perfect. sorry for my confusion at the outset. Actually tracking down the right question. All right. And now I'm looking back at my handwriting. I think you did say 2, and I just wrote something that looked like a 7 by accident. All right, so Ashel had the question about integrals, and we also had Amy's question about some practice problems, Unit 1 and Unit 2. Amy, I think you had the first question in there earlier, so I'm going to take a look at some of those first. Let me just confirm that we have this correct. Unit 1, 32 and 55. And Unit 2, number 9 and 22. If that's incorrect, please confirm either way, I guess is my recommendation. And again, I'm just trying to find a way to see the earlier comments. As opposed to just the last 5. Let me try something different here. Look at that. Okay, we got some more here. All right. Okay, so Amy, there we go. All right, so Amy, I found your questions there. Let me just confirm. 32, 55, 9, 22. Perfect. Okay. For these, again, just in the interest of being the most helpful, if you can let me know what the issue was with these questions, like was it just I don't even understand what it's about, or was it I got halfway through it, or I got a different answer? That really helps us narrow down on what the actual issue is. All right. 32. 32. Okay. All right. So 32 is a question of nesting functions. It's these guys here. For this one, the procedure is always going to be the same. Sorry, I'm just scrolling back through the comments here. Okay. Literally with this notation here, you take 3 as your input, and then you run that into the G function. So we go over to our G, and we have the challenge of counting some web work intervals here, but I go over 1, 2, and 3, and we'd find that the Y value there is, it looks like negative 1.5. This is 1, that's 0, that's negative 1. So negative 1.5 would be the Y value. Then we would take that and put it into as the input to the F value. So if we actually did this mechanically, we would do F of G of 3. This part here from the graph is equal to negative 1.5. So this is equal to F of negative 1.5. And that is a lookup on the F graph. On the F graph, we go to negative 1, we go to negative 1.5, and we would be around here. You count some lines. I think these are tenths. So you'd basically be at negative 1, 2, 3, 4, or something like that. Actually, probably negative 0.3. We could get a little more sophisticated finding the actual formulas for these slopes, but that's the process. On an exam, we'd either give you a more detailed graph with nicer numbers, or we'd ask you, or would accept values that are reasonable. Anything from minus 0.3 to 0.5 here is probably in the ballpark of what you're going to get. But the key thing is just that sequential process, start at 3. That's the input for a function. Look that value up in the graph. Once you had that, it becomes the input for the next function. Look that up on the graph, and so on. All right. If you have any follow-up questions, please just put them in the comments as well. I'm able to see those a bit better now. And 55. All right, so I was reading over the question here. Sorry, it's up here for those who are following at home. All right, so this is, again, an interpretation question. Just how do you use functions? So the key thing here is the input. At time t hours after taking a cough suppressant, the t shows up in the exponent over there. Then the a value is how much you're going to have of this cough suppressant in your body, remaining in your body. So I'm tempted not to go through all these 4 parts, just in the interest of time. If there's a specific part you'd like to look at, can you let me know? I'll just pause for a moment here for you to take a look. And again, I'm just trying to make sure I'm not missing any comments. There we go. I think I'm saturating my poor connection to the internet here, so let's go here. Just B and C. Perfect, thanks. Okay. That wasn't showing up earlier. All right, so for part B, let's take a look at that. We would have number 55, and you have A is equal to 10, 0.83 to the T. For part B, if you're being asked what percentage leaves the body, you can actually look at this right away and see it. So I'm going to show you what I would interpret here, having seen exponential functions more than most. Just remembering how this number appears. This 0.83 is, it's usually constructed by a subtraction. It's sort of by default, if I put a number 1 in here, then I have a power that doesn't change anything. Everything we talk about relative to that is relative to 1. So the way you get 0.83 is 1 minus 0.17. And the way I would interpret that is I'm going to have the same amount minus 17% per hour. So that would be my quick and dirty calculation that would give me the answer to this question. It's really not the only way. The other way that's maybe a bit more procedural is to compare A at t equals 0 and t equals 1 and literally compute the difference in percentages. So if we do that, at time 0, we have 10 times 0.83 to the 0. That 0.83 is just a 1. And so we have 10, and I believe it's milligrams. Milligrams, yep. But A of 1 hour later, we have 10 to the 0.83 to the power 1. If you multiply that out, it's 8.3 milligrams. So we went from here to here, and we dropped, do the subtraction, 1.7 milligrams from 10 milligrams. So the percentage drop is 1.7 over 10 times that 100% scaling factor to make it a percentage. And surprise, surprise, it ends up exactly at 17% there again. Another way to think of it, we're keeping, after each hour, we only keep 83% of what we have. If we're only keeping 83%, we're losing 17% every hour. So that would be my rationale for that question. Please, again, feel free to comment if there's something in there you'd like to investigate further. For part C, again, we'll need our formula. 0.83 to the t. How much of the dose is left in the body 8 hours after the dose is administered? So the most common thing here is to overthink it. What we're going to do is simply plug in the number t equals 8. So we're going to have 10, 0.83 to the power 8 instead of just t, and whatever that value ends up as. So yeah, that's my calculator. The part D is more complicated because you have to actually solve stuff, but here it's literally subbing in the number and seeing what you get back. So 2.253 milligrams approximately would be the answer for that one. How does that sound? Any follow-ups on that? Sorry, I know I'm recognizing there's a long lag between me saying something and it actually appearing on the screen or the voice coming through. So I'm giving some pauses after questions to let that catch up. All right. I'll continue on then to Unit 2, number 9 and 22. All right. Number 9. Okay, for number 9, there's also a lot of subparts. So if you can let me know which parts of that you'd like to look at. And for number 22, okay. Number 22 is a long one. We'll definitely do that one. But let me know about the number 9 one first. We're going to pause on 22, though, and there was another question in between, just in the interest of sharing the wealth around here. This was Anshul's question about the integral. So let's do a question here. So, Anshul, I'm guessing this is based on a web work question. Is that the case? The integral of e to the 7x sine of 2x. Oh, okay, perfect. Okay, so we'll do 22 as well. All right. Sorry if that was framing. Okay. So the best guide for this is, I'm trying to think where it is. It would be Unit 11. I'm just going to take a look down here. Get the solutions up. I think it's right at the very end of this, just before the applications. Right. So the model for this is number 37 from the practice problems, where we, actually 37 or the one before it, actually, I think 38 is essentially identical. So e to the x times sine of x. So in a question on an exam for this, we would actually give you the tip of compute this integral by using integration by parts twice. That's exactly what happens with the question you're asking here. The only difference is that you have some constants as well. So I'm just going to take a quick look at that. The nice thing about this, maybe surprisingly, is it doesn't matter which function you call u and which part you call dv, as long as you do the same thing twice. Let's just, in the interest of actually, no, it's easier to differentiate sine and cos without making a mistake about the plus and minus stuff. So let's do it this way. And as soon as you make that call, then the follow-up comes naturally after that. We get the derivative of the first term, and then we integrate both of the second term. So we get v equals 1/7. When we integrate, we end up dividing by those kinds of constants. And then we cross multiply. And we're going to call this integral I, just so we don't have to copy it down every time. When we do that, we get e to the 7x minus, I'm going to take a couple of shortcuts here just in the interest of space. There's two numbers, the 2 and the 1/7. They're going to come out front. And then we're going to have e to the 7x cos of 2x. All right. Sorry, I just saw Patrick's comment there. We can absolutely do that. Test 2, number 3. Okay. So what we've done here is we've traded the original integral for a new one, but it's certainly not simpler. It's different, but it's not simpler. But what we try to do is do the same thing again. So I'm going to call this thing here I2, just so we don't have to, again, carry all the baggage from before. And if we do the same integration by parts, and the key thing here is to choose the same assignment. So we made our trig function u last time. Let's make the trig function u again. And we make our exponential, the v part, the dv part, and the dx. We integrate that. We differentiate this with respect to x. And we get ourselves a -2 sine of 2x. And over here, we get a 1/7 e to the 7x again. And we cross multiply, and it's all good. So this time I will copy everything down. So we have 1/7 sine of 2x e to the 7x minus 2/7 times what we just found here, the cos and a 1/7. So I'll just bring the 1/7 out. Cos of 2x e to the 7x minus the integral of the v times du. Again, I'm going to take a little shortcut. There's a double negative, so it'll be a plus. And there's a 2/7. We can bring that out front as well. And we're going to end up with e to the 7x sine of 2x dx. Close that big bracket. Now that looks horrible. I will grant you that completely. The major observation, and the reason we covered this in one of the videos and also included in the practice problems, is that there is a common strategy you can use for this, and that's why we'd give you the hint about integrating by parts twice. What we've done is we've gotten back to where we started. That integral that we have is exactly what we call the thing we want to know. What's the integral of e to the 7x sine of 2x? And so the freaky thing is we can just rename that and call it I. And then we look to the left-hand side and we're like, hey, I've got an I over here. So even though I haven't solved the integral, I haven't gotten to the end and sort of finished, what we can do is actually solve for I, which is our integral that we want, and nothing else requires integration. So I'm just going to copy this over to the next page, and we'll see how that plays out. Move that up to there. So the way we'd write this is what we want to know is I, and it's equal to 1/7 sine of 2x e to the 7x. Write a bit bigger clearly here. I'll get all the constants sorted out here. minus 2 over 49 cos of 2x e to the 7x, and then being very careful here, minus 4 over 49 i's. And that major observation is that we can then bring this over to the other side. Here we have 1i, and I'm going to add 40. I'm going to add 4 over 49ths. So we're going to have 49 over 49 plus 4 over 49, all those i's, equals what we just said before, the sine 2x e to the 7x minus 2 over 49 cos of 2x e to the 7x, and whatever this fraction is here, you bring it to the other side, and boom, you have the I equals, but your I is literally what we meant by the thing we asked you to calculate, e to the 7x integral 2x dx. And that's getting a little scrawly, my apologies. 2x dx. What is that, 53? So 49 over 53 times this whole conglomeration here. Not bad. All right, close. So that's how you can take an alternative approach to evaluating an integral. Notice why it works. When we integrate sine, we have this cycle that it goes to cos and then back to sine again. So we do return to the start. And as we integrate or differentiate e to the 7x, we always get e to the 7x. It's a pretty distinctive pattern. That combination of functions is special in the fact that we can do this and get back to where we started. This would not work with x squared. Because of x squared, we keep differentiating, it eventually goes away. So it looks very different when we try to evaluate those kinds of integrals. But with this particular combination of e to the something and sine of something or cos something, there's a repetition in how the derivatives and integrals work that you get back to where you started after a bit, and that gives you this interesting way to work around the function. All right, so I'm just going to pause the audio for a sec because I'm going to have to cough. I'm just catching up for Ethan there. The solutions are all posted. Let me actually show this to you. It's probably easier than trying to explain it. Just do a save here. And here we go. So this might take a second or two just because my internet is being somewhat crippled by the video projection. But if you go into OnQ, which will load here momentarily, then there's a page called Exam Information off the front page, very similar to where we had the term test information. I'll highlight it here. So there's an exam information page there on the right-hand side. And if you click that link, you will find the old exams with solutions. So there's the blank exams and the exams with solutions. Say you're working on the 2015 exam. You get to here and assume everything loads. There we go. We have brief explanations for the multiple choice and the answers, and for the long answer questions, we have the worked out solutions as well. So all of that is available anytime between now and the exam. Alrighty. So, sorry, I'm just going back. So I've got Pendle's question and Patrick Lee's and also Amy's last one question there. So Amy, will do your last question, unit 2, number 22, which I can put up here. Yeah, so we'll erase that. So Unit 222 was a relatively complicated limit question for sure. I'm just going to bring up the actual question text here. All right. It's very much in the feel of some of the other limit questions, though, so that should give you some grounding for it. So we've got limit 5 to kx. Limit as x goes to infinity, 5 to the kx over 5 to the 4x, I believe. Yeah, plus 5 plus 7. And the idea here is that these are exponentials. They're not powers of x. So we can't divide by the highest power, which is what we would have recommended in those scenarios. But at the end of the day, this feels like it's approaching infinity over infinity. Why? Because these powers of 5 would be getting larger and larger in principle. So how did we fight that in the past? Well, we did divide by sort of the biggest power, but here what we can do is divide top and bottom by the same thing. What's making things complicated is we have a k in here. I would just take the easier version. Just why put more k's into things? Let's divide by 5 to the 4x. If we do that, then you can simplify your ratio. I'm going to do everything but that first term. You'll see why in a second. 5 to the 4x, and 7 over 5 to the 4x, and this turns into a 1. That's why we do that. So this is really, really nice. This new form here doesn't, it has a lot of terms that go to 0, which is kind of what we'd want. 5 to the 4x is going to get bigger. It's in the denominator, goes to 0. That goes to 0. That's just a 1. So everything hinges on the ratio you have in that first term in the calculation or in the expression. So what we have for that is basically a new problem. So we know what everything else is doing. So the new question is, what's the limit as x goes to infinity of 5 to the kx over 5 to the 4x? And there's any number of ways you can do this. Well, not any number, there's about 2 or 3 ways to tackle this. In some ways, I think it's easiest to use your exponential rules to say, well, if I have a power in the top and a power that I'm dividing by with the same base, then I can simply subtract the exponents. And that's not super helpful out of the gate, but what it lets you do is then factor out an x. And sorry, I've realized I committed a mistake that we usually discourage students from. I want to find all these things still with the limit as x goes to infinity. Okay. Okay. So again, please do interject in the comments if anything comes up there. So this is a whole different question, and it's actually a lot simpler in some ways. However, it does require thinking about this k thing, which often students find challenging just because it seems so abstract. You're like, what is k? Well, if you just think about what happens with limits, if you just have a limit as x goes to infinity of 5 to the x, that's going to go to infinity because you have 5 and you're taking larger and larger powers of it. Is there ever a time where it doesn't go to infinity? Absolutely. If we had 5 to the negative x, well, that's like 1 over 5 to the x. Well, that goes to 0. Well, what's the difference between those two scenarios? Well, it's not just that it's x and negative x. I could put a 2x in here, or I could put a 0.5x. The key thing is that you have some positive number times x. If you have some positive number times x in the exponent, your exponential is a positive exponential that corresponds to exponential growth, and the limit is going to be infinitely large. Whereas if you put a negative in here times x, let's clear this up a little bit. Well, that's exponential decay, and we know what that goes. It always goes to 0. Well, what plays the role of that multiplier in this particular question is the k minus 4. So if we have k minus 4 positive, that leads to growth, and that leads to the limit is infinity or does not exist. It does not exist. If k minus 4 is negative, less than 0, then we get decay, and the limit exists, and more specifically equals 0. And so that's what boils down to the calculations you see in the solutions to the practice problems. You'll have, translating this into nicer form, if k is 4, you're going to get growth. The limit does not exist. If you have k less than 4, then you're going to get decay. The limit exists, and that boils down to the solutions that we have included online. Let me just pause there for, again, that's a challenging question for a lot of people. So other people might have inputs as well as Amy. Okay. I will leave that question at that point then. Oh, sorry. Right, there's that transition point. If k equals 4, what I would actually be tempted to do is go back to the original question, because specific cases like that, if you had k equals 4, then you can actually do the limit because you have the same expression in the numerator denominator. I think you'd get 1 at the end, yeah, because you divide top and bottom by 5 to the 4x. This would be a more traditional kind of calculation, like with powers. You end up getting 1 plus 5 over whatever, over 1 plus 7 over whatever. You take the limit, it heads towards 1 over 1, which equals 1, which exists as well. So you would get k less than 4 exists and k equals 4 exists, the limit exists, whereas k greater than 4, it does not. Perfect. So I just saw Amar's question there, 11B from Unit 5. Okay. So I'll leave that there for a moment. Excuse me. And let's take a quick look at test 2, number 3 for Patrick. Then we'll do Pendle's question number 10 from a multiple choice. And sorry to put Amar's name on there. I apologize for any mispronunciations of names with Unit 5, 11B. We'll start with Patrick's test 2, number 3, which is, as he pointed out, the same essentially as the practice problem, I think 37 from Unit 7. But let's bring that up first. Actually, I think right now, sorry, let me give, I don't know where the questions are. Oh, I have it open. Here we go. We'll just do a quick scope through on cue here. Come on. That's the exams, not the exams. We want the tests. As on cue gradually loads, here we go. On cue loads, turn tests. Oh, there was an error someone just pointed out yesterday. It hadn't come up before then. In one of the, just the final answer number in this question. So it may be, let me know if that's the issue. But the process was all correct. It was just a final calculation silliness. Question 2, question 3. All right. So again, this was for Patrick, is there any specific part of this that you wanted to look at? If there is, I'm going to start copying the question over, but if there's something particular, please feel free to add that in the comments. All right. So not quite perfect shape here, but you get the idea. All right, we got this dividing line. And it was a 5 by 12 triangle thing here, except this is actually a cylinder inside rather than being just a rectangle. All right. So, doing question there. 3. Sure, absolutely, Angela. I just saw your thing there. Okay. So, in all these optimization questions, the first goal is to remember what do you want to optimize. We want to optimize the volume. We want the max volume. That's what we want. To be able to get that, then we need a formula for the volume, which fortunately is not too hard because it's just a circle that's being stretched out, circle area being stretched out by height h. I'm going to add those to the diagram here. This length here is r. Now, if I wanted to make the volume really big, I'd make, say, my radius really big, but I can't make it any bigger than what fits inside this structure, this cone. So what it boils down to is there's a limit on r because of my choice of h. So somehow h and r are related. I can't just pick them both however I like. So how do we do that? Well, we look at the picture and go, I see a right angle triangle in here. And there's a few different ways we can use right angle triangles, but to me, what makes the most sense is similar triangles. The other two options would have been trig functions, but here I wouldn't use that because we don't have any angle information and we don't really care about the angles. We could also use Pythagoras, but that doesn't make any sense because we don't care or have any values for the hypotenuse. However, similar triangles, that sounds like a winner because I can see a small triangle here and I can see a big triangle on the outside and the ratios of those triangles will be the same, et cetera, et cetera. So we're in business if we start using that. So let's take a look and dive into that part of it. We have the small triangle, do it in red here, and we have the big triangle in green. The green triangle we know everything about. It is 5 at the bottom, it is 12 along the top or the vertical side. The red one's a little tougher. It certainly has the radius, going up to our first diagram, the radius of our cylinder is going to be r at the bottom there. But the vertical height is not something we have already. What we have instead is the whole thing's 12, but then I'm going to subtract h. And so what I'm going to get here is 12 minus h. All right. So 12 minus h is what's left over as the height for that smaller triangle, which is similar. You're like, oh, there's an h, there's an r. I was interested in how those two things are related, so we can take a look at that. It's totally up to you how you go from here, though. I tend to do ratios like r to h here, so r over 12 minus h is the same as the ratio from 5 to 12, and then swap around however you like. 12 r's are the same as 5 times 12 minus h, and I guess we might as well isolate for r because it's right there. 5/12, 12 minus h. And so that is a major landmark. We can use that in our volume calculation now. So as soon as you tell me what the height is, I also know what the radius is because it's constrained by the height. And so we get our new volume expression, pi times a whole bunch of things squared, and that whole bunch of things is 5/12, 12 minus h, all squared. And that tends to be the most challenging thing for most people. After this, it's a traditional optimization problem of find the derivative. Here it's with respect to h, and set it equal to 0 to find critical points. Let me know if you want me to dive into that part, but typically that's what most students are comfortable with, the differentiation and solving process. It's setting up the equations in the first place. That tends to be where the questions arise. So let me know if that's the case for you. And Anshul, if you have a follow-up question about that, please do. Okay, and I just saw Kyle's question about families of functions. Absolutely, happy to do that. There are certainly some in the last couple of years, maybe not last year, but the year before, like 2016's exam. If there's a piece of that you can sort of carve off and sort of say, this part here is what I'm interested in, that would really help sort of focus it. Right, so how do you know it's a global? So yeah, there's two follow-up questions to this: global maximum versus local maximum. And so that's not the right way. Let's do this. So to find local max, or to confirm that the point that you found is a local max, it's enough to do the first or second derivative test. Derivative test. Either one is fine. They both tell you whether something's a local max or local min, or neither. Or we could ask for global max, and I think that was in one of the old exams as well. For global max, we actually only have one technique for that, and it only works, requires that V here is defined on a closed and bounded interval. It turns out that is the case, or you can make a case for that here. The h values, yeah, this whole height here was 12. So h has to be less than 12, and h has to be, worst case, 0 would be the other end of this. So we can say, yes, we have a closed and bounded interval. Sorry, there's our h. And if that's the case, we have a closed and bounded interval, check. Then the global max occurs at either a critical point or an endpoint. And so literally for those, you can calculate the V when h is 0. That's going to be 0 volume, as it turns out. V at h equals 12 at the other end. That'll also give you a super thin cylinder. The V is 0. Meanwhile, the V at, sorry, look at the solutions here. H is 4. When you do h is 4, you get some volume that's not 0. Not sure if we actually calculated it or not. Yeah, we didn't calculate it. But it's some number that's positive. And of those three things, this is the largest. So is the global max for volume. So that would be how we would do the global max argument there. Okay. Okay, Kyla, thanks. I saw your note there. I'm going to dive into that link in a second. Okay, so I'm just going to add that to my to-do list here. Concavity. All right. So up next, just for catching people's ears, let me go to the end here. There we go. So Pendle had a question from the 2016 online version of the exam, which may or may not be the same as the main campus. Don't get surprised, someone else, if you haven't seen the question. And then Amar's question about Unit 11B, Unit 5, 11B, and then we'll take a look at Kyle's question after that. So that'll be our order right now, is Pendle. 2016 MC from the online exam, number 10. Oops, that was weird. Don't happen there. Pardon me for one sec. What is going on? Fascinating. Just going to save that. We'll just restart our PDF annotator here. Oh, got an idea. That's messed up. All right. Not enjoying that at all. Give me one moment here. I'll just close that the old-fashioned way. There we go. All right. 2. All right. We're in the technical glitch there. We're just going to bring back the annotating software and then dive right back into those. Not quite sure what happened to that first bit. All right. All right. Okay, bottom. Fantastic. All right, we are back in business. So yeah, the 2016 and then MR's and then Kyle's. 2016, all exams old. All right. CDS. All right. Oops, question 10, pardon me. Okay, that's weird. So I'm just looking for Pendle's question, but I only see 9 questions in the PDF file, which is very strange because we always have 10 multiple choice questions. Let me just check the solutions. Let's see if something happened in between those two things. There we go. All right. Average of a function. Let me just confirm that that's the one you're asking about. Sorry for the audio, changing screens. Okay. Full size here. So I'll just pause for a second here to confirm that it's the average value function that you were asking about. This is for Pendle. Perfect. Okay, let's dive in. All right. So the function was 4 minus x minus 1 squared. Oh, right, because you're asking about the breaking into pieces. Okay. So that's your function. And then the average value of that we can plug into our formula, or you can reason it through, whichever you like. It's that integral, and then we divide by the interval size. And sorry, the question was between 0 and 2. Sorry, between 0 and 2. So the integral goes from 0 to 2, and this is 2 minus 0. And away we go. So yes, absolutely. I should actually put brackets here to indicate that this is all times dx. But you can absolutely break this into the integral of 4 from 0 to 2 dx minus the integral of the x minus 1 squared from 0 to 2 dx. In fact, I would encourage that because that's how you sort of think about it. So just going down this, you'd have 4x between 2 and 0 minus x minus 1 cubed over 3 between 2 and 0, and do whatever subbing in you like. 4 times 2 is 8, minus 0, minus, I'd probably keep it at the third, 2 minus 1 cubed, minus 0 minus 1 cubed. This one I have to be a bit more careful about. 8 minus 1/3. Oh, that's just 1. So 1 minus 1. Okay, so that's just 2. So we get 8 minus, so we get all the negatives correct. I think we get 8 minus 2/3 as the value of the integral, which I'm just going to do a quick calculation. That'll be 22/3. 22/3. And then we also divide by 2. So the average is going to be 22/6. Sorry, do it right here. 22/3. That's the averaging part. Sorry, the half is averaging the total area. And so you end up with 22/6 or 11/3. I'm just going to confirm that matches our answer. 11/3, perfect, yeah. So for this particular problem, the goal is just to be able to do the integral, like I said, in 2 pieces, and also not to forget that the integral is related to the average value, but it's not equal to the average value. Oh, sorry, I just saw Kyle's question there. You can integrate this however you like. If you wanted to expand this and integrate 4 minus x squared plus 2x minus, it'd be a double negative, so minus 1, which is the integral from 0 to 2 of minus x squared plus 2x plus 3. Sure, it'll give you the same answer. Doesn't matter. What you're doing isn't changing anything. So yeah, however you want to integrate it, as long as you can be confident that what you're saying is the antiderivative of what we gave you or something equal to it, then absolutely, whatever occurs to you. If it's a polynomial, there's about 2 or 3 different ways you can probably tackle it each time. That's fine. So I'm just seeing a pause occurring in the video feed here. I think we're maybe catching up. I'm just going to try refreshing my viewing page here for a second. No, not good. Okay. Pardon me. It's helpful for me to have confirmation there. Okay, there we go. We're caught up. Okay. My guess is probably just a negative sign somewhere, because there's literally no difference between the function there and the function here except how it's written. So I'd be a little bit careful about the negative on that guy and making sure that you subtracted 1 at the end of the day. It's really easy to lose the negative multiplier for the x minus 1. That's all. That's all. And yes, confusing or switching gears between derivatives and integrals is one of the single hardest things to get right. Now that especially when we're doing it back and forth, as you do integration by parts or integration by substitution. So yeah, that can be a real challenge. I'm totally sympathetic with that. Okay. Yes, there's the derivative. Okay. All right, so next up was Amar's Unit 5, 11b. Let's track that down. Unit 5, 11, 11b. The vertical tangent line. Okay. Let's take a quick dive into that. So this is Unit 5, 11b. So we have to do a bit of 11a just to get to what the ingredients here. x squared plus y squared minus 2x minus 4y equals negative, doesn't matter because it's going to go away when we differentiate, minus 1. And again, if you have any questions along the way, MR, please, or comments, just let me know. So what we would do traditionally with this is we would, we're being asked about slope values. So we would differentiate both sides with respect to x and do that implicit differentiation process. So hopefully we'd agree on this. We get 2x, y with the x derivative gives us an extra thing for the chain rule, dy dx, or if you like, y prime. I don't care, but I usually write dy dx just because it stands out more. And then 4 dy dx's, and the right-hand side is just 0. Just gonna get rid of that guy. And the question B is asking for vertical tangent lines. And there's a few different ways to talk about this, but honestly, I think the easiest, if we think about some surface, some curve that's being implicitly defined, then what's special about the vertical tangent is that dy dx is technically infinite, but positive, negative, safer to say does not exist. There's no single numerical slope for this because you're dividing by 0. There's no run, there's only rise. A whole bunch of ways to look at it. So that's going to be what we're looking for. We're going to be looking for points where dy dx is undefined. And if that's the case, then how are we going to track that down? Well, we can isolate dy dx. We have 2 y's of them minus a 4. If I bring everything to the other side, I'll have negative 2x plus 2, or dy dx equals negative 2x plus 2 all over 2y minus 4. And then we just use that condition. Hey, when is this ever going to blow up? Well, the only way to blow up this particular calculation is to have dy dx is going to be and does not exist only when the denominator equals 0. The numerator, any x will do, it'll always give me a number back, but I definitely cannot divide by 0. And so that would give you the condition. So 2y minus 4 equals 0 is what we get from this. And so 2y equals 4, y equals 2. That would be the y coordinate, which leads to dy dx undefined. Now, it'd be nicer to have a bit stronger argument for that. When we talk about 0 slopes, it's super convincing. There's a lot of ways, though, for something to not exist, but this would be sort of the level of analysis we would be looking for in this class. Is vertical tangent lines have no numerical slope value. It's not slope 1, 2, a million. The slope value is literally undefined or does not exist. Once we get our slope formula, how can I make it not exist? Well, I can divide by 0 in this case here. Okay, so I just saw Angela's question related to this theme, and we might as well follow up on this next, and then we'll dive into Kyle's just because we're doing implicit differentiation right now. Yeah, I'm going to pause here for any follow-up questions on that. And the feed seems to be taking quite a while to get out there. I think it's like 20 seconds behind. Perfect. Okay. Love the thumbs up. Thanks, Amar. All right. Let's take a look at the other question that Angela just asked. It was from Web Work from Unit 5. And had the same kind of flavor, except x squared plus 4y squared. equals 36. And you want the points where the tangent line goes through 12, comma 3. All right. For this, I think it really, really helps to have a picture. So this whole surface here shouldn't come as a huge surprise because it's like x squared plus y squared equals r squared. It's like a circle formula, except there's a little 4 here. So it shouldn't come as a huge surprise that it's an ellipse. So it's some kind of, I don't know, either flattened or tall ellipse, but it's kind of circular-ish. We have our point 12,3 way the heck over here. And there's going to be some points where if I draw the tangent line, let's draw a bigger target. If we draw the tangent line here and maybe over here, that we're just going to go through that point 12,3. And our goal is to identify the locations on the ellipse that lead to that sort of sequence. Well, how do we do that? This is very similar to some of the questions in the previous unit when we did actually more unit 3 with tangent lines. So what we would need to do right away is basically define this location. Let's call this the point A comma B. So I don't know where it is, but I need some coordinates for it. And if it's ever helpful, I know that it's on the ellipse. So a squared plus 4b squared is going to equal 36. Because it's on the ellipse, so it has to satisfy the original equation. All right. For the tangent line, what we need is a slope and a point. Now, in some sense, we have the point already. The point's the point AB. The slope we're going to have to get, and it's going to be something we get through implicit derivatives. So what we're going to do is we're going to take our x squared plus 4y squared equals 36, and we're going to take some derivatives. One of each side, both with respect to x, like so. And just like the last problem, I won't belabor it, we're going to get 8y dy dx's, that's our slope, equals 0. And so dy dx is equal to minus 2x. Let's do it in stages. Dy dx is going to be minus 2x over 8y's, or minus a quarter x over y. All right. Again, please feel free to jump in with a comment if there's anything that sounds fishy there. I am seeing a tremendous lag here. It's fascinating. Please let me know if you have any issues at your end with the audio or anything else. I'm definitely having some trouble refreshing the page at this point, which is odd. Like I've filled up a whole page by the time this thing's catching up with me. So I'm going to keep going, but please do interrupt. Is it okay? Maybe it's lag as opposed to non-smoothness. We'll go with it. Thanks for the feedback. All right. So our tangent line then at the point AB is going to be y equals, and just remember the ingredients here is going to be slope. Well, we just said our slope was negative. Oh, we said negative x over y, but we're doing it at the point AB. Sorry, try to keep my colors consistent here. And sorry, 1/4. Negative 1 over 4y. Was it negative? Yeah, it was negative. Okay. Times x minus the x coordinates, that's x minus a, plus the y coordinate plus a b. Alrighty. So that looks a little horrible, but in some sense, it fits our story of you tell me where you are on the ellipse, the point AB, and I'll tell you the formula for that tangent line. I've got the slope, I've got it going through the point AB, all the ingredients are in there. So we're good. We're going to give it a go. The only thing that we want special out of this line is that it go through the point 12, 3. Well that, if we take a look at our generic formula here, that means when I plug in x equals 3 on my line formula, sorry, when I plug in x equals 12, let's get the formula right here, I get y of 3 back. And now all of a sudden, we have reduced our equation to something that is just in A and B. And I'm really, really hoping that we're going to be able to get rid of even one of the other ones as we do that. Remember, we're trying to solve for A and B. Solve for A and B. And that can feel a bit problematic at this stage because I have A's and B's, but remember, we also have our other tool in our back pocket that A and B aren't random with relation to each other. They're the X and Y coordinates on the ellipse. So we also have that to fall back on. So the game, I think right now, is to try to get these two equations into each other. Let's try this first. Just try expanding stuff. Actually, yeah. Let's go this way. I'm going to bring the b to the other side. 3 minus b is minus a over 4b. So this is trial and error, honestly. Like, how can you tidy this equation up? I just hate denominators when we're doing this kind of solving. So let's multiply this up. We have 3 minus b times 4b's equals minus 12a minus a squared. And what do we get here? We get 12b minus 4b squared. Now that looks a bit horrible. Did I get my signs right? Oh, this is plus. There we go, plus. But, phew. Okay, I see a light at the end of the tunnel. 4b squared, I'm going to move it over, and I'm going to move the 12a over. So 12b, is that going to work? Plus 12a. Let's try. Let's see what happens. B squared. I was hoping for something more exciting than this. This is an exact match to the formula in our equation. So we actually have this whole thing equals 36. Sorry, just had a chance to look up. Thanks for the update on the feed there. And like I say, the video feed doesn't have to be super good, so as long as the audio is coming through relatively clearly. Interesting. So we get 12b plus 12a is equal to 36. I'm just scanning. This question is very carefully crafted so that the answer does pop out nicely. And I'm just trying to think where when I've done this previously, we just got a equals something. So I'm feeling like there's a typo somewhere in my solution at the moment. I'm just trying to track it down because the problem is we still have two variables left. It's not a showstopper, but it would be nice to have something a little nicer than that. So I'm just scanning for errors, typos, that kind of thing. If you spot one, let me know. And sorry, Megan, I just saw your note. Yeah, we can definitely take a look at that Newton's method question. Okay, I'm staring at this. Let me just make sure I got the actual formulas right here. 3. Yep, that works out. So what I'm thinking right now is one of the answers is right at the top of this ellipse at the point 0, 3, works like a charm. And that does work with this equation. If we pick b equals 0, sorry, b equals 3 and a equals 0, we get an answer. and it also satisfies the equation up there. But the other solution is not as obvious, and I thought it fell out a lot more easily than this is. Let me just take a quick scan back here. B, that's fine. I know it's super exciting to watch someone else get stuck on a problem. Hopefully it makes you feel comfortable about the whole process. Yeah, I thought one of these A's and B's fell out. I guess no, it's linear. Oh, I think, okay, sorry, this is how, sorry, I just got there, finally got there. This is totally fine. We divide everything by 3, and we get this, and then we can sub this into the other equation, like 3 minus b. We take this and we stick it into here. Of course. Sorry, I say of course as if it's obvious, but of course that was 3 minutes of staring at a page. Once we get this, we can plug it in the other equation and we get a nice quadratic. So if we combine those two ingredients, a equals 3 minus b into our a squared plus 4b squared equals 36, put those together, we get 3 minus b squared plus 4b squared equals 36. It's a nice quadratic. I'm going to just expand that out. 6b plus b squared plus 4b squared equals 36. There we go. I'm going to write it in a more traditional order. B squared first. 9 minus 36 is 25. 36, 25, sorry, 27. Minus 27 equals 0. And then you can use your quadratic formula. 6 plus or minus the square root of blah, blah, blah. And you can solve for your a and b that way. So I think we're in business there. Let's just confirm that it actually gives us the right answer before I get too hasty with this. B squared 36 minus 4a. Careful with the negatives. We should get 2 nice values. Actually, it doesn't make sense. Sorry, I'm just going to do a little side calculation because I know b equals 3 has to be an answer. Times 9 times 18. Oh, it is. Okay. Sorry. I shouldn't sound as excited as this, but I am excited. All right, over 2 b's. It's just a horrible way to get there. So 6 over 10 plus or minus. What do we get here? 5 times 4 times 27 is 540. So 36 plus 540. Oops. Take a square root of that. Should be something nice. 24. Aha. There we go. If we do a quick check on that, so we're going to get 30 over 10, or, oh, nice, or minus 24 minus 18 over 10. That's our 3, and the minus, however you want to do it, 9/5 or whatever. Then we can get our a value from the earlier equation, 3 minus b. So a is going to be 0, or a equals 3 minus b. Is that right? Negative, yeah, okay. Minus 9, 3 plus 9 over 5. 24 over 5. So the 2 points would be 0, 3, and 24 over 5 minus 9 over 5. And those do make sense, thank goodness. Draw our ellipse here. Here's the point 12, 3. If we draw our tangent line there, and somewhere down here in the bottom quadrant is the kind of thing we're looking for. When we draw that tangent line, we will actually find the point whose tangent line also goes through the point 12, 3. Whew. All right. That was that ordeal right there. You guys are picking excellent questions for the level of detail. If you're feeling comfortable with the material just on the cusp of these ones, then you're in excellent shape for the exam. I would say these are on the harder end of the kinds of things we would ever expect on the exam. All right, I'm going to pause there for a sec, and then we'll dive into. Shoot, I've lost track of it. I had someone's. Kyle's? No. So we got Megan's question on the list. Oh, Kyle, you had the question about the concavity. Right, that's what it was. Okay, Megan's after that. All right. So let me just bring that question up there. This is from Kyle. And it was a web work question, I think. Oh no, this was an exam question, wasn't it? Yeah, because we gave you f double prime. F double prime of x is equal to 4 over x minus 3 all over 9 times 2 minus x to the 5/3. 5/3, right. And correct me if I'm wrong, but the goal here was to do a sign chart so that we could determine the concavity levels. Oh, you're welcome, Angela. Right. Homework. Sorry, I just saw Theo's question there. The question about the homework, just be more specific. There's practice problems and there's web work. Neither one's technically homework. So yes, absolutely yes. If you can just let us know exactly what question you're referring to, then we're good to go. Okay, so the concavities. So for these kinds of questions, the first thing I'd be looking at are points where f double prime equals 0. And that's sort of what everybody would usually look like. And we can actually see that pretty quickly here. X equals 3 is going to be a breakpoint for that just because of the x minus 3 on the top. However, you also have to consider f double prime undefined, because if there's a place where things blow up or are undefined, then on either side, let me just do a quick sketch here. So the graph of, let's do 1 over x. 1 over x? Yeah, let's do 1 over x. The graph of 1 over x looks like this. It's undefined at 0, and it changes concavity. It's concave down on this side and concave up on this side. So it's not just enough to know that this never equals 0, so it never changes concavity, looking at the second derivative, but points where things get undefined are also possible transition points. So with that in mind, we also look for where this is undefined, and it'll be undefined when we divide by 0, and that will be when x equals 2. So basically we have 2 landmarks. Let me put them up top, actually, 2 and 3. And after that, we trust at some point that you've learned how to build a sign chart. My preferred way is to look at all the ingredients, and in particular look at, so here look at x minus 3, and look at 2 minus x to the 5/3, and basically figure out what the sign is for each of those, and then we figure out the sign of the whole thing, f double prime. And we just do that on each interval. So for x minus 3, you can plug in numbers. Some people like doing that, so they plug in a number like 0. 0 minus 3 is negative, so that means on this entire interval all the way up to 2, it's going to be negative. You can plug in a number like 2.5 minus 3, oh, that's negative 2. But then after 3, if I plug in a number like 4, I get 4 minus 1, that'll be positive. And so we get that kind of chain of signs. Okay. Now the 5/3 thing, I will completely agree, is a bit touchier. 5/3 here. The key thing to remember is that this is essentially an odd power. So whatever sign you get on the inside, take it to the 5/3, it'll stay the same sign. So you plug in a number like 0, you get 2 minus 0, that's positive. You plug in a number like 2.5, then 2.2 minus 2.5 is negative. And you're going to get another negative there. And then you just combine those together. if I have a negative, so I'm going back to my original expression up top here, I'm basically dividing or multiplying. So I just take the product of the signs. So this will be negative, this will be positive, and that'll be negative. And this translates to concave down, concave up, and concave down. So that would be the sequence of steps I would do to do the concavity analysis once you have a formula for the second derivative. I'll just pause there. And I just saw Theo's question there, just copying that down. Unit 1068. 1068. Sorry. I think my feed has given up. Sorry, I'm just looking at the old screen and it's still showing the last question. So I'm just going to pretend that you guys are all fine. Let me know if it's not fine at your end. And I'll just focus on the comments that you're posting. All right, families, root b minus x. Yes, so that does happen when you have constants, but not numbers. So like bx e to the x minus a or something like that. So the challenge, let me go back. What I would usually do for those is, let's actually swap this out. Let's call this a and b, and my order's wrong here, so I'm going to call it b and a just to match what we had before, b and a. So the challenge with that is not to get distracted by the fact that it's a constant. Somewhere we would have said that a is less than b or something. All the analysis we just did, you don't actually have to do with a number. It's nice, you can type it into your calculator, it's safer. But if I tell you, let's look at this interval over here, I've got a number that's super big. And my calculation is take that super big number and subtract b from it. Well, b is smaller. I can see that in my real line. So on this range, x minus b is going to be something positive. As soon as I get numbers that are less than b on this range, I'm taking a small number minus b. Well, b is bigger. I'm going to get these two negative signs. I don't know how better to express what's actually going on in the mental process there, but that's literally it. All the expressions we're looking at tend to be of the am I bigger than x? Oh, sorry, is x bigger than b or is x less than? Actually, that's maybe a better way to do it. You can actually rephrase this as x larger than, sorry, x equals b. X equals b? What am I trying to say here? I'm interested in if this is larger than 0. That's going to be the case if x is larger than b. When x is bigger than b, that's this, I'm not sure this is helping. When x is bigger than b, I'm over here, and I get a positive value for that expression. I'm not convinced this is helping at all. If I want it less than 0, so where do I put my negative signs? Well, I'm going to put my negative signs when x is less than b. Oh, well, that's all this stuff. So I put negative signs when x is less than b. That's an alternative approach to that. Oh, good. I just learned a comment about making a lot of sense. Okay. Yeah, that's, if you have to, on a side page, please not on the exam. We do take marks off for this. But if you do a little side calculation and say, oh, let's just pretend it's 2 and 3 for a second, and I'm going to plug in 2.5 and then go, hey, it's negative. As long as you're consistent about doing that and translating it back to your original sign chart, we're never going to know how you got these signs. If you just kind of write them down, this is the kind of thing we expect some students can do in their head, so no explanations required, as long as you get it right. So yeah, just do a little side calculation, do it that way, and that would be fine. Okay, so sorry, we had Megan's question and then Theo's Unit 10 question. Megan, I'm just scrolling. Pardon me. I'm just scrolling back up to your thing because it was longer, as I recall. Right. Right. It was the Newton's method. Okay. 2016 number 4. 2016 number 4. I'm assuming this is the on-campus exam then. Sorry, let me just get the exam up here. Nope, that's not it. Use Newton's method. Oh, maybe section 4? No, it said multiple choice. Sorry, Megan, if you can let me know whether you're on campus. Oh, sorry, there it is. Right in front of me, number 6. Okay. I don't know where I got number 4 from. Number 6, approximation of value. Okay. So the equation was, so this is multiple choice 2016 number 6. E to the x equals 1 plus x. And we're going to start at x equals 1. Yes? Yeah. I'm sorry, the question was the next iteration? Second approximation, yeah. So Newton's method, 2 things. We need to build our f of x. 1 function only. Our current formula has 2 things. It has both sides of the equation. So we're going to have to move everything to one side, and that's going to be our function. And we also need the derivative f prime of x. So we're going to need f prime of x. Let's find f prime of x. It's going to be e to the x again, 0 minus 1. So those are our 2 ingredients. All right. So those 2 ingredients we then put together with the Newton's method formula. So Newton's method formula, try to write that somewhat legibly there. Formula is our x new is, I'm just going to call it current x minus f of x over f prime of x. So we just sub in the values, and hopefully we get what you have listed as an option, and we'll just see if that actually pans out. So for us, it's going to be 1 minus, put this all in brackets, our function was e to the 1 minus 1 minus 1 all over the derivative e to the 1. I think this is just a simplification problem, is the most likely guess here. So we get 1 minus e minus 2 all over e minus 1. That would be a perfectly valid, correct answer, but that's not one of the options we have in our list. So we're asking for a little bit of extra calculation here. All the terms there had a common denominator, so let's make a common denominator here. Let's bring it up to here. So we'll have e minus 1 minus e minus 2 all over e minus 1. And then we have, if we expand everything out, let's be super careful with our signs here, plus 2 over e minus 1. There we go. E's cancel. We end up with just plus 1 on top. And I think that was answer D. Oh, C. There we go. 1 over e minus 1, which was C. So I think it was just a question of simplification after that point. Let me know if you have any follow-ups on that one, or if that made sense. In the meantime, I'm going to get Theo's question, Unit 10, number 68. 1068, okay. We do not have Unit 10 open, so I'll just get that going. $68. Okay. Okay. Excellent. You're welcome, Megan. So Theo, which element of this question were you looking at? Because it's basically three ways to get to the same thing, but it might look different is essentially what that's boiling down to. Okay. Glutton for punishment. Okay. So A and B, I'm just thinking realistically, most people's focus is on the exam preparation. 68 A and B are totally legitimate exam type questions, just like the earlier question. I think it was Ashtul who asked about the Anshul, sorry, who asked about the circular integration by parts. A and B are exactly that, so those make sense. C is, we haven't done a huge number of trig substitution kind of things, so it's less representative, but A and B are actually fairly straightforward and are fair game. So I'll do those parts first and just see how it works out. Sine of x, cos of x, dx. Alrighty, so your choice. So I think we actually gave you a little hint here. You probably said, okay. So yeah, let's make substitution. Right, sorry, not by parts. I was thinking substitution. Yes, right. It's coming back to me. So let's let w equal cos of x. Sorry, sine of x, I said. Dx. Sorry. So this is a substitution, not by parts. So the derivative is cos of x. And if that's the case, we can then reshuffle this and say 1 over cos of x dw is the same as what we have in our equation. There's our dx. So we have the integral of not sine of x anymore. We're calling it w. We do have the cos of x. That was in the equation. But then we have dx, which is 1 over cos of x dw. And the beautiful thing about that is now the cosines cancel. That's lovely. I'm sorry, this is nothing like the circular example I was talking about earlier. My bad. I apologize. This is actually easier in a lot of ways. We get w squared over 2 plus c, so we get sine squared of x over 2 plus c. And you think, okay, that's lovely. I've found my integral. And then we get into this game that they're playing with b, which is, hey, you didn't have to do it that way. In fact, there's a really nice observation that you could have let w be the cosine and things should still have worked out largely the same way. The only difference is we get a negative sign creeping in here. So negative 1 over sine of x dw is equal to dx. So we have a new dx formula here. We also have a new w. I'm going to need to do this on another page. Yeah, we're going to do this on another page. I'm just going to, so free stream that in your mind. We're going to be doing this integral. I'll copy that over onto the new page. Oops, copy this. Oop. So this with our w equals cos of x and negative 1 over sine of x dw equals dx. Now we can do our substitution. We did not substitute for sine. We did substitute for cos. Now it's a big W. And we get the cancellation happening over here. dw. Now these guys cancel. And we get, that was weird, we get the integral negative w dw. No, wait, that's what we just saw before. W squared over 2 plus c but this time that's negative cos squared of x over 2 plus c. Now, like, hold on. We also have this supposedly equal to sine squared of x over 2 plus c, and those do not look the same. So the question is, oh, did you find your error? I just saw your comment there. Yeah, the short answer is you can use the trig identity. Hey, cos squared plus sine squared, sorry, x equals 1. So I can actually swap this out. Sine squared of x equals 1 minus cos squared of x. So you can turn this into 1 over 2 minus cos squared, cos squared of x over 2 plus a c. Oh, that's negative cos squared of x over 2 plus c plus a half. Well, let's just be a little bit careful here. My constants don't have to be the same. These are the same now, except this c2 is this c plus a half. They're off by a constant, but that's allowed because we don't know what the constant is. As long as the functions agree, then we're okay at the end of the day. Okay. I don't know what untrue means. Alrighty. Okay. I think, unless I missed somebody, which is entirely possible. If it is, please do re-comment. But that was so far all the questions that I had in my queue from you guys. Any new arrivals? Anybody else have a different question that hasn't been covered yet? Feel free to just type that in the comments. You know I'm going to be Googling that later, right? Okay. I'm not seeing any new comments. I'm just going to try refreshing one last time here. Question 3 from term test 2. Sorry, I just hit refresh and I saw some comments appear and now they're hidden for a moment. I think we did question 3 from test 2 a little bit earlier. So let's just go back a few pages. Given that, what I'm going to try to do, and what Facebook tells me in principle is possible, is that I can download the video for this. And if I can do that, what I'll do is just cut it up into pieces. And basically, where there's a coherent answer to a question, including that test 2 number 3, I'll be able to either give you a timestamp for that or a separate video, probably just a timestamp, I think. So basically, once the video recording is up, I'll try to add a comment so you'll be able to go back to that question. But we definitely did question 3 from test 2 a little bit earlier. Sorry, there. Sorry, I just got Megan's first part there. Okay. The one that has the antiderivative graphs. Yes, absolutely. again, if you just say main or online, that'll tell me which version of the exam we're talking about. But they're highly similar, but not perfectly identical, as we have discovered. There we go. Okay. All right. So this one is making me wish I had better screen capture tools so we could cut and paste it. All right. Okay, so the first issue with this one is just, sorry, getting myself back in the headspace. So the things that I'm thinking whenever we have a graph like this, and I will do a quick note here, just go down to the end, some space. All right, new page. All right, so what we have is 2016 multiple choice number 10. We have a graph, and the graph looks like little bulb, and then larger, and then X4 comes back up. Okay, so something like that, X4. And the only reason we put those little labels on is to help when the graphs don't vertically line up. So honestly, I would probably try to sketch this graph myself and its antiderivative, where this is g of x, and then this is the antiderivative. The steps, the two things that are crucial are that y values on this graph translate to slopes on the graph down here. And the other element is that areas, more specifically integrals, those translate to changes in y values here. And also, if it helps, think of this as velocity and this as your position. So you can tell a little story even from the outset. I'm going to move forward for a bit, and then I'm going to stop. All these zero values are stopping motion. Then I'm going to move backwards for a bit, and then I'm going to stop, and then I'm going to move forwards for a bit. So if you think about that, it often helps to anchor what you're sketching down here. The third element is that it doesn't matter where you start. You can start anywhere on this line because antiderivatives have a plus c. That lets you shift the graph around wherever you like. I'm going to start here and just pick one of the random points. So I'm going to go forward or away for a bit. Sorry, I'm going to start with zero slope because there's a zero value first. So values, slopes. Then I'm going to have positive values until I get to x2. And then I have a zero slope again, or I moved away for a bit, and then I'm going to move backwards. So I'm going to move negative values for a bit until I get to here, something like this, until I get a zero slope again, and then I'm going to have positive slopes after that. So at a rough sketch, that's what it's going to look like there. For this kind of multiple choice question, that's probably a good thing to do anyway, even though you can, let's see if this actually is enough to answer the question. Let's go back. In fact, yeah, there's only one graph that kind of does that. It's really this graph here. If I'm looking for the anchor points, so we had up and then down and a zero slope, the anchor points that I used were that at x0, x2, and x4, my graph had zero slopes. The only ones that have that are, oops, downside of not having an annotator here. Sorry. There we go. The points that had zero slope at x2 and x4 is this one. This one sort of maybe does, but it also has a zero slope here, which makes no sense. This one makes no sense because there's no zero slope at x2. This one has no, yeah, it has to be D, just from what we sketched before. That's the only one that completely matches the lineup of the locations of those local maxes and mins, those critical points, with the information we were given about g of x. So I'm going to pause there for a sec. Does that make sense? Okay, you're welcome. I'm happy to take one last question. I'm not too worried about the 2 o'clock end time. So any other questions people are thinking about right now before you get back to this studying or other studying? Okay, I'm not seeing too many responses to that, which is excellent. And the questions that you were asking were definitely ones that were on the sophisticated end, so that's a good sign for preparation. If you do have any other questions, just a reminder that we'll be running sessions like this tomorrow and Tuesday as well, same time, 12 to noon, or sorry, noon till 2 p.m., just to avoid any conflict with other exams. You can join later if you have a morning exam, for example. That's totally fine. And yeah, otherwise, good luck with the rest of your studying. Thank you guys for coming out.